Friends, welcome to this lecture. Today we are going to learn regarding the abstractions from precipitation, or we can call it as a losses from precipitation. What is evaporation? Evaporation is the process in which liquid changes to the gaseous state at the free surface below the boiling point through the transfer of heat energy. Consider a body of water in a pond. The molecules of water are in a constant motion with wide range of instantaneous velocities. An addition of heat causes this range and average speed to increase. When some of molecules possess sufficient kinetic energy, they may cross over the water surface. Similarly, the atmosphere in the immediate neighborhood of water surface contains molecules within the water vapor in motion, and some of them may penetrate the water surface. The net escape of water molecules from the liquid state to gaseous state constitutes evaporation. Evaporation is a cooling process in that the latent heat of vaporization at about 585 calories per gram of evaporated water must be provided by the water body. Losses from precipitation. When any resource engineer while calculating precipitation minus runoff is equal to losses, that is a state equation. Precipitation minus surface runoff is equal to total losses. An important one, that total losses is equal to evaporation plus transpiration plus interception plus depression storage plus infiltration. So here you can see the measure is evaporation here in the total losses. The rate of evaporation is dependent on various factors, or we can call it as a factors affecting evaporation. First one is the vapor pressures at the water surface and air above, air and water temperatures, wind speed, atmospheric pressure, quality of water, and size of water body. Now let's see one by one. First one is the vapor pressure. The rate of evaporation is proportional to the difference between the saturation vapor pressure at a water temperature EW and the actual pressure in the air EA. Thus, EL is equal to C into bracket EW minus EA, where EL is rate of evaporation millimeter per day and C is the constant. EW and EA are in mm of mercury. Remember this always, EW and EA are in mm in mercury. In above equation is known as Dalton's law of evaporation after John Dalton 1802, who first recognized this law. Evaporation continues till EW is equal to EA. If EW greater than EA, condensation takes place. Please remember this. Second is temperature. Other factors remaining the same, the rate of evaporation increases with an increase in the water temperature. Regarding air temperature, although there is a general increase in the evaporation rate with increasing temperature, a high correlation between evaporation rate and air temperature does not exist. Thus, for the same mean monthly temperature, it is possible to have evaporation to different degrees in a lake in different months. Third is the wind. Wind aids in removing the evaporated water vapor from the zone of evaporation and consequently creates greater scope for evaporation. However, if the wind velocity is large enough to remove all the evaporated water vapor, any further increase in wind velocity does not influence the evaporation. Thus, the rate of evaporation increases with the wind speed up to a critical speed beyond which any further increase in the wind speed has no influence on the evaporation rate. This critical wind speed value is a function of the size of water surface. For larger water bodies, high speed turbulent winds are needed to cause maximum rate of evaporation. Next is atmospheric pressure. Other factors remaining same, a decrease in barometric pressure as in high altitudes increases evaporation. 4 is the soluble salts. When a solute is dissolved in water, the vapor pressure of solution is less than that of pure water and hence causes reduction in rate of evaporation. The percent reduction in evaporation approximately corresponds to percentage increase in the specific gravity. Thus, for example, under identical conditions, evaporation from seawater is about 2 to 3% less than that of fresh water. Next is heat storage in water bodies. Deep water bodies have more heat storage than shallow ones. A deep lake may store radiation energy received in summer and release it in winter, causing less evaporation in summer and more evaporation in winter compared to a shallow lake exposed to similar situation. However, the effect of heat storage is essentially to change the seasonal evaporation rates, and the annual evaporation rate is seldom affected. Now, next important point is a measurement or estimation of evaporation. So, for that we will have to learn evaporimeters. Estimation of evaporation is the utmost importance in many hydrologic problems associated with planning and operation of reservoirs and irrigation systems. In arid zones, the estimation of is particularly important to conserve the scarce water resources. However, the extent or exact measurement of evaporation from a large body of water indeed one of the most difficult tasks. The amount of water evaporated from a water surface is estimated by the following methods. First one is using evaporimeter data. Evaporating data. Second is empirical evaporation equations and analytical methods. Types of evaporimeters. Evaporimeters are water containing pans which are exposed to the atmosphere, and the loss of water by evaporation is measured in them at regular intervals. Meteorological data such as humidity, wind movement, air and water temperatures and precipitations are also noted along with evaporation measurements. First one is a class A evaporation pan. It is a standard pan of 1210 mm diameter and 255 mm depth used by the US Weather Bureau and is known as Class A land pan. The depth of water maintained between 18 cm to 20 cm as shown in the figure. The pan is normally made of unpainted galvanized iron sheet. Monel method is used where corrosion is a problem. The pan is placed on a wooden platform of 15 cm height above the ground to allow the free circulation of air. Below the pan, evaporation measurements are made by measuring the depth of water with a hook gauge in a stilling well. So, you can see the cross section of this evaporation pan. Here you can see this wooden support is provided here. Remember the dimensions, the depth is 255 and the diameter is 1210 mm, 1210. Okay, and the water level is shown here, and you can see the pictorial view of this pan. So the evaporation calculation, this is one of the important device, you can say. Then ISI standard pan. This pan evaporimeter specified by IS 5973 in 1970, also known as modified class A pan, consists of a pan 1220 mm in diameter with 255 mm depth. The pan is of copper sheet of fine 9 mm thickness, tinned inside and painted white outside, as shown in the figure. A fixed point gauge indicates the level of water. A calibrated cylindrical measure is used to add or remove the water, maintaining the water level in the pan to a fixed mark. The top of pan is covered fully with a hexagonal wire netting of galvanized iron to protect the water in the pan from birds. Further, the presence of a wire mesh makes the water temperature more uniform during the day and night. The evaporation from this pan is found to be less by about 14% compared to that from an unscreened pan. The pan is placed over a square wooden platform of 1225 mm width and 100 mm height to enable circulation of air underneath the pan. So here you can see the pictorial view of a pan evaporimeter. So also you can see the cross section of this standard evaporation pan. Okay, so you remember the dimensions, so 1225. Okay, and you can see the depth is a 255 here. Okay, so you can see the adjacent, it is provided with the thermometer, and thermometer clamp is provided here. Okay, then it is a copper sheet of a thickness 0.9 mm. Okay, so and stilling wheel is provided here at this position and having a fixed point gauge, and at the top here wire mesh cover is provided. Okay, and at the bottom wooden platform is provided to support that. The next is a Colorado sunken pan. This pan 920 mm square and 460 mm deep is made of unpainted galvanized iron sheet and buried into the ground with 100 mm of the top. Okay, you can see in the figure the chief advantage of the sunken pan is that radiation and aerodynamic characteristics are similar to those of lake. However, it has following disadvantage: it's difficult to detect the leaks, extra care is needed to keep the surrounding area free from tall grasses and dust, etc., and expensive to install. So you can see the cross section of a Colorado sunken pan. The 920 mm is square is there, and 460 mm depth is there. Okay, this is the water level, and this is a pictorial view of this Colorado sunken evaporation pan. Next, we will move to the US Geological Survey floating pan. With a view to simulate the characteristics of a large body of water, this square pan of 900 mm side and 450 mm depth, supported by drum floats in the middle of the raft, 4.25 meter by 4.87 meter, is set to set afloat in a lake. The water level in the pan is kept at the same level as lake, leaving a rim of 75 mm. Diagonal baffles provided in the pan to reduce the surging in the pan due to wave action. Its high cost of installation and maintenance, together with difficulty involved in performing measurements, are its main disadvantages. So you can see here this particular floating pan is there. Okay, and cross section of that, but you can see the pictorial view also, how it floats on the water, and it is a square pan especially, and as stated here, the disadvantages are difficulty involved in performing the measurements, and its because of its construction, high costs in installation and maintenance together. Then let's move to the next part as a pan coefficient Cp. Evaporation pans are not exact models of a large reservoirs and have following principal drawbacks. First one, they differ in the heat storing capacity and heat transfer from sides and bottom. The sunken pan and the floating pan aim to reduce the deficiency. As a result of this factor, the evaporation from a pan depends to a certain extent on its size. While a pan of 3 meter diameter is known to give a value which is about the same from neighboring lake, large lake, and a pan of 1 meter diameter size indicates about 20% excess evaporation than that of a 3 meter diameter pan. Second is the height of rim in an evaporation pan affects the wind action over the surface. Also, it casts a shadow of variable magnitudes over the water surface. Third one is the heat transfer characteristics of a pan material is difficult from that of reservoir. In the view of the above, the evaporation observed from a pan has to be corrected to get the from lake under similar climatic exposure, and thus coefficient is introduced as a lake evaporation Cp into pan evaporation, and in the Cp is equal to pan coefficient. Now these values in the Cp in used to different values are there. So the values of the pan coefficient Cp, you can see the 4 types are there. Class A land pan, which is 0.7, ISI pan modified class A 0.8, Colorado sunken pan 0.78, and USGS floating pan is 0.80. Evaporation stations. It is usual to install the evaporation pans in such a locations where meteorological data are also simultaneously collected. The WMO recommends the minimum network of evaporometer stations as below. Arid zones 1 station for 30,000 km square, humid temperature climates 1 station for every 50,000 km square, cold regions 1 station for every 1 lakh km square. Currently 220 pan evaporometer stations are being maintained by the India Meteorological Department. A typical hydrometeorological stations contains ordinary rain gauge, recording rain gauge, Stevenson box with maximum and minimum thermometer, and dry and wet bulb thermometers, wind anemometer, wind direction indicator, sunshine recorder, thermohydrograph, and pan evaporometer. Now some empirical evaporation equations. The general formula which is used, a large number of empirical equations are available to estimate a lake evaporation using commonly available meteorological data. The most formulae are based on Dalton type equations and can be expressed as a general form. EL is equal to KF U in the bracket again EW minus EA, where EL is lake evaporation in mm per day, EW is equal to saturated vapor pressure at the water surface temperature in mm of mercury, EA actual vapor pressure of overlying air at a specified height in mm of mercury, FU that is equal to wind speed correction function, and K is a coefficient. The term EA is measured at same height at which the wind speed is measured. So remember this EW and EA because these are again used in the further empirical equations. Now again the two commonly used empirical evaporation formula are Mayer's formula, which is constituted in 1915. EL is equal to Km in the bracket EW minus EA into bracket 1 plus again U9 divided by 16 bracket complete, in which EL, EW, EA are defined as earlier equation. U9 is a monthly mean wind velocity in the kilometer per hour, at the 9 meter above the ground, and km is the coefficient accounting for various other factors, with a value of 0.36 for the large deep waters and 0.5 for small shallow waters. Then next one is the Rover's formula, which is constituted in 1931. Rover's formula considers correlation for effect of pressure in addition to the wind speed effect, and is given by EL is equal to 0.771 in the bracket 1.465 minus 0.000732 PA into bracket 0.44 plus 0.0733 U naught bracket complete into bracket EW minus EA, where EL, EW and EA as specified in earlier equations. PA is the mean barometric reading in mm of mercury, and U naught is equal to mean wind velocity in kilometer per hour at ground level, which can be taken to the velocity of 0.6 meter above the ground. So today we have discussed regarding the evaporation, what is the effect on the total losses, how to calculate the evaporation, and some empirical equations. So again in the coming lectures we are going to study regarding the infiltration and associated examples. Thank you very much for joining this session.